Okay, so this is a review of thermodynamics. In particular, we're going to look at the first law of thermodynamics, which is going to be concerned with total internal energy. So temperature is a measure of the average energy of molecules in a system. Total energy is a measure of just all of them put together. And there's two ways to change that. Heat, which is the transfer of thermal energy, and then work, which is changing the volume of the gas in that system. So with that, let's do thermodynamics. So when we talk about systems, a system is basically just what you're studying. Now, a closed system is one in thermodynamics that's pretty important because it does not exchange mass with the surroundings. That's important there because if you have mass exchange, like if you just put a gas in air with no container around it, it's just going to expand forever outwards. So a closed system, the gas can expand, but it's not going to leave the container. However, a closed system, and this is going to be as opposed to an isolated system, you can have heat enter and leave, but not mass. So there's a couple of important variables for thermodynamics. They're all forms of energy. The first one we'll look at is total internal energy. So temperature was a measure of the average kinetic energy of the molecules in a gas. The total internal energy is just all those molecules put together, their total kinetic energy. So the total internal energy is going to be equal to U, which is equal to capital N times K average. Now, capital N there, that is the number of molecules. And then K average, that's the kinetic energy for each molecule. So they give us the total energy. And we can write it this way. So this is N number of molecules times K average, which we got when we did thermal physics. That's 3/2 Boltzmann constant times temperature. I mean, that is a formula you can use. There is a more common version, and what that does is it uses two things. So U here, the number of molecules is N times Na. So little n here, this is the number of moles. And Na here, that's Avogadro's number. I'm not going to write that because then I cannot spell Avogadro's number. So I have 3/2. The Boltzmann constant, there's another form of the Boltzmann constant. It is the universal gas constant R over Avogadro's number. So Avogadro's number cancels out. And then the other form of this equation is U is 3/2 nRT. And that's a formula that's good to have. It's on the formula sheet for the total internal energy of a gas. In a thermodynamic process, you're usually looking at the change in internal energy between different steps of the process. So internal energy is basically a measure of total energy of all the molecules. So it's going to be directly correlated to temperature. So if your change in internal energy is positive, that means that the internal energy is increasing, which means that the temperature is increasing. If the change in internal energy is negative, that means that that energy is decreasing, and therefore the temperature is decreasing. So delta U is positive, the molecules are getting faster. Delta U is negative, the molecules are getting slower. There's two other variables that change in different steps of a thermodynamic process. So the next one is heat, which is also a form of energy. It's thermal energy. And heat can also be positive or negative. So if heat is positive, that means that you have heat going into the system. And if heat is negative, that means that the heat is leaving the system. The next quantity that's going to be important for thermodynamic processes is work. Now we know from anywhere in physics that work is force times distance. So when gas is in a container and the container is pushed down or it expands, you're going to have a force being applied, so that's F, over a distance delta x, and force applied over distance is work, so we have work being done, which is F times delta x. Now in this case it's negative delta x because the container is being pushed in, so that's a negative displacement. And then we're trying to relate that to pressure because we're doing thermodynamics. So pressure is force over area, which means that force is pressure times area. So work is pressure times area times negative delta x. Now let's look at A delta x. So this little change in volume here, well, it is a change in volume because I have a cross-sectional area and I have a height, so that's a little cylindrical change in volume. So A delta X is our change in volume. So our work is going to be negative P delta V. And that is the work in regards to thermodynamics. It's also written in upper level physics as this, which means in physics 2, that's the area under a P versus V graph. And that's work. One of the most difficult parts in thermodynamics is determining whether work is positive or negative. So on the left, that's positive work. Now, positive work is when an outside force is doing work on the gas, as in is compressing the gas. So when a gas is compressed, that's positive work. Conversely, when a gas expands, that's when the gas is actually pushing outwards. The gas is doing the work, so work done by a gas, that's negative work. Now, it's easy enough to remember compression positive, expansion negative, but it's important to understand why we have positive and negative work here. So in physics in general, work is equal to the change in energy. So in the case of positive work, when the gas expands, the gas molecules are going to move faster. So they're gaining internal energy. That's how we have positive work being done. When the molecules expand outwards, they're having to do work, and in order to do that work, they have to expend their internal energy. So when a gas expands, it's losing energy, which is why that's negative work. Here is the first law of thermodynamics. Now, this is just conservation of energy. So all three things in this equation are just forms of energy, and they're changes in energy. So we have delta U, we have Q, and we have W. Delta U, that's the change in internal energy, and you really want to think of that as temperature. What's happening to the overall temperature in the system. So if delta U is positive, you have an increase in temperature and increase in internal energy. If delta U is negative, then you have a decrease in temperature and a decrease in internal energy. So Q is heat added. So if Q is positive, that's heat added to the system. If Q is negative, that's heat removed from the system. And then W is work. This is the tricky one because in IB physics, they use the opposite sign. But if W is positive here, work is done on the system. The gas is compressed. If work is negative, then work is done by the system, as in the gas is doing work, the gas expands. And then here's what that means in terms of words. So this is the AP physics version of the formula. So delta U, the internal energy, that'll increase. So it's directly proportional to two things. Heat, if you add heat, so if heat increases, that's going to increase delta U. Obviously, if you add heat to something, it's going to get a higher temperature. And the other thing, this one's a bit more confusing, work. If you do work on the system, so if you compress a system, if you do work on the system, that's also going to increase the temperature. If you think about like a container, if you press the gas in the container, the gas is going to be moving around more because it's hitting the walls more. So you're going to have an increased temperature. Now that's the AP physics way of looking at the formula. IB physics has a different way of looking at the formula, which I think for me makes more sense. So here's the sort of IB physics formula. This one says heat added equals the change in internal energy minus the work. And this says if you add heat to a system, you can do one of two things. So obviously you add heat to something, if heat increases, then the temperature is going to increase. You add heat, something gets hotter. That one makes a lot of sense. The other one says if you add heat to a system, then that's going to lead to work being done by the gas. So if you add heat to a gas, it's going to move around more because it's getting more energy, and it's going to expand outwards. Right, so those are the two things that happen when you add heat to a system. So go ahead and look at a demo of that right now. Here's a closed system. It's got the little balloon on it, so it's closed. And then here's heat. It's boiling water on one of the least used stoves in America. And when I add heat to the water bottle, putting it in the water, so I'm adding heat, so that's going to do two things. It's going to increase the temperature of the water bottle. The water bottle is obviously getting hotter. And then the volume is expanding because the balloon just got bigger. This shows what happens inside the bottle. So I add heat to the bottle, and as a result, the gas expands, so the gas does work, and the molecules move faster, so it's increasing internal energy. A big thing in AP physics is pressure versus volume graphs. known as PV diagrams. So let's look at a couple here. So I have a pressure versus volume graph here and a pressure versus volume graph here. So we know that when work is positive or negative. So work is positive when a gas is being compressed and negative when a gas is expanding. So I have a graph that in any way moves to the right. So I have a graph like this. That means the gas is expanding. That's negative work. And then if I have a graph that goes any way to the left, so I have a graph like that, that's the gas being compressed, so that's positive work. And then where people get mixed up is when you have a graph for a complete process. So let's say I have a process that's clockwise. So we'll take this one for example. So let's just look at the top and bottom branches here. So this top branch here is negative work. Bottom branch is positive work. Now, the negative work is above the positive work, so it's greater. So if you have a clockwise PV diagram, that's going to be corresponding to negative work. And then the reverse of that, if I have a counterclockwise graph, I have my positive work up here, my negative work down here, so any counterclockwise graphs can be positive work. And then on this graph as well, there's a vertical line here. A vertical line, there's no change in volume. So a vertical line, that's going to be zero work. There are 4 types of thermodynamic processes you should know about, and those are isochoric, adiabatic, isothermal, and isobaric. Here they are in a PV diagram. The first one to look at is isochoric. This is also called an isovolumetric process, and based on that name, you can probably guess what it is. It's a process with constant volume. So that means that the change in volume over this process is 0. And then the work done on or by a gas is P delta V. Well, if there's no change in volume, there's no force over a distance, the work is 0. And from the first law of thermodynamics, which says that delta U is Q plus W, if W is 0, then Q equals delta U. Now, what that means is any heat that you add is just going to increase the temperature. So if I increase the heat, I'm going to increase the temperature, and vice versa. So if I have a gas moving around, if I add heat to it, there's nowhere for it to go, so it's just going to get faster. And likewise, if a gas loses heat, then it's going to lose energy and get slower. Okay, so on a PV diagram, it's pretty easy to know when the process is isovolumetric. It's just going to be the same volume. And it's just a vertical line because it's always going to have the same x value because volume's on your x-axis. All right, isobaric process. Now this one's a bit hard to maintain. As you expand a system or contract a system, it's hard to keep the same pressure. So that's why in the diagram you see that there's heat being added in order to keep the pressure constant as the gas expands. And this one, you can't really cross anything out in the formula, but for this one you can definitely use the fact that work is P delta V, and we're in AP physics, so it's negative P delta V. And that's because the pressure is going to be constant. And in this case, you have temperature and volume being directly proportional. And it's pretty easy to know what the graph is going to look like here. This graph is just a horizontal line because the pressure is going to be constant. The next type of process is an isothermal process. So iso, same, thermal, temperature. This is a process where the temperature remains the same. So temperature is kind of based on the internal energy. So in an isothermal process, delta U, the change in internal energy, is going to be 0. Now looking at the first law, delta U equals Q plus W. If delta U is 0, then Q is simply negative W. What that means is if you add heat to the system, well then you get negative W, which means the gas is expanding, the gas is doing work. So in this kind of process, heat added is going to expand the gas. And what that looks like on a PV diagram, it's going to be sort of a little swoop going along that way. So as the gas expands, there's going to be less pressure. The final type is an adiabatic process. Now in an adiabatic process, there's no heat added to or removed, so that's Q. So in this process, Q is 0. And then going back to the first law, you have delta U, which is the change in energy equals the work done. So this is where you either compress or expand the gas, and as a result, the temperature is going to change. And this is going to be another swoop on the PV diagram. This one's going to be steeper, and we'll look at why that is. Here's a look at what's actually going on in an adiabatic process. So let's look at adiabatic compression. So in adiabatic compression, you have an outside force compressing the gas. Now, since a force is doing work, that means that there's a transfer energy. So that energy is transferred from the outside force to the gas. And as a result, the gas is going to speed up. And that's because the molecules in the gas are going to collide more as they're in a smaller container. So adiabatic compression is pretty simple to kind of comprehend. Adiabatic expansion is a bit more complicated. So in compression, we had work being converted to energy. In expansion now, the gas is doing work. Now, in physics, you can't do work without energy. So in adiabatic expansion, the gas molecules are going to slow down. And the reason why they slow down is they're losing energy. They're expanding, which means they're doing work. You have to get energy from somewhere to do work, and the energy comes from their internal energy. And this is why adiabatic curves are steeper. So isothermal curves and adiabatic curves are both those sort of, they're curvy on a PV diagram. And to tell the difference, adiabatic curves are steeper, and that's because as adiabatic expansion happens, you're going to have the gas molecules slow down, so they're going to collide less with the container, so you're going to have an even steeper drop in pressure. Whereas in isothermal curve, the gas molecules are going to collide less frequently because the container's bigger, but they're going the same speed, they're not going to slow down, so they're going to collide more frequently than an adiabatic curve. The most common thermodynamics free response question on the AP exam is usually going to be something involving a PV diagram. So here's a question where we have 1 mole of an ideal gas, so N is 1. It's taken through the process A, B, C, A, so that means it goes from A to A through B and C. We're given the temperature at point A of T sub 0, then we have 4 questions there. So part A asks for the temperature at B and C, and that's going to be in terms of the temperature at A, which is T sub 0. So the most helpful formula you're going to have is PIV equals nRT. So we're solving for temperature. We have P and V for all these points. We know N is 1 because it was given, and R is a constant, and we're going to leave it as R because it's a fundamental constant. So solving that for T, you get PV over NR. So we can go ahead and find the temperature at each point. We'll start with point A. So at point A, it's 2P because the pressure is 2P. The volume at A is 1 over R. And we were given the temperature, it was T sub 0, but we know T sub 0 is equal to 2 PV over R, and we're going to calculate B and C in terms of T sub 0. So TB, again, you look at the pressure and the volume at B, it has a volume of 2V and a pressure of just P, and you get 2P over R, so that's equal to the temperature at A. So if A is T sub 0, then B is also T sub 0. Now for C. So C has a pressure of P, a volume of V, so its temperature is PV over R. Okay, so A is what we're given. A is T sub 0, it's 2P over R. So our temperature at C is just half of that. So the temperature at C is T sub 0 over 2. All right, part B is pretty easy. Is the process isothermal? Yes, it was, because we got that temperature at A was T sub 0. Temperature at B was T sub 0. Isothermal means same temperature. So yes, that was an isothermal process because both those points are at the same temperature. Okay, what's the work done by the gas during BC? So this is a graph of pressure versus volume. Something about the work done here. Pressure is going to be the integral of P dV. Now, Physics 2 is an algebra-based course. So in Physics 2, anytime we see an integral, it's just the area under the graph. So we're going to do the area under the graph from B to C. Now, from B to C, the work is positive because we established that positive work means the gas is being compressed. This one here, the volume is decreasing. That means the gas is being compressed. That means the work is positive. And I guess we didn't even need to know that. We just have the formula, equals negative P delta V. If you use delta V, you're going to have small thing minus big thing. So there we go. It's negative P. And then V final minus V initial is V minus 2V. So the work is positive PV from B to C. Okay, D, what is the net heat added to or removed from the gas? This is just for one complete cycle. So let's look at going from point A to point A. So what's the net heat added to or removed from the gas from point A to point A? Well, what we know from point A to point A, if we go all the way around the graph from A to A, we know that delta U, because point A is at a certain temperature, so the change in internal energy from A to A is going to be 0. And then we can't calculate the heat from the graph, but we can find the work from the graph. So work for a single process is the area under the graph. Work for an entire process is the area of the graph, so it's the area of this triangle here. And this is negative work because A to B here, this is negative work, and that's going to be a greater magnitude than B to C. So B to C is positive work, but it's below the graph from AB. So the net work's going to be negative, and of course, C to A, there's no work because there's no change in volume. And the work's the area of the graph, so it's the area of that triangle. And of course, the area of a triangle is 1/2 base times height. The height goes from P to 2V, so it's P. The base is V to 2V, so it's V. And the area is PV over 2, so the work is negative PV over 2. Now we'll find Q from the first law. So the first law says delta U equals Q plus W, and we know that delta U here is 0. So then Q is negative W, so if work is negative PV over 2, then the heat added to the gas is PV over 2. So in this cycle here, since there was no change in temperature, since there was negative work done, that means there was heat added to the gas. All right, and that's thermodynamics, or at least the first law of thermodynamics. We don't have to talk too much about the second law. The second law is just entropy. It says that over time there's more disorder, but that is thermodynamics.